Okay, sorry to cut off that powerful music. That's Bach, and I thought it would be appropriate here because we're going to move on to Gauss's theorem, which is a kind of a powerful theorem on electrostatics. All these wires they put that into for us to trip over. It's unbelievable. First I wanted, however, to just touch up a little bit of the last lecture. I got to the point where we had discussed materials, and they come basically in three varieties in a way that one way of categorizing them. One is insulating, meaning that the I actually thought of an analogy. Insulators are kind of like married people, where the plus and minuses are sort of we're strongly bound to each other, and it takes a lot, hopefully, to separate them. So they're kind of married. Whereas conductors, you have, they're sort of free to wander a little bit. And almost if you think of it this way, when you put them in fields, like if you put, this is actually sort of heterosexual, I'm sorry to say, but whatever. You see the minuses are going to run to the pluses, and the pluses are going to run to the minuses. And these people are rather free to travel, whereas the married folks, if you do a similar thing, well, they may be inclined that way, but they shouldn't go all the way. So if you want, think of these as married and these as more or less single. And I think you'll get to the answer pretty quickly, depending on your inclinations, your impressions of single versus married people. But it actually works because you see, you put these here, and they may be inclined that way. And it's like if there's a party and there's a lot of pluses here, and the group of married people is sort of near there, they may go, well, let's go to that party because it's nearby. And they may stay for a while, but they won't interchange too much. They won't exchange charges too much because, shouldn't anyhow. You know how it is. Whereas the single folks, when they get over here, these guys see somebody they like, and they're going to jump over, and then once these negatives are depleted, they say, oh, that too many of those pluses over there. Let's go to the other party. You've been there. and that's more or less how it works. So the insulators are more or less the married folks, and there's a whole category. Among them are the simple dielectrics, of which these are married couples, and they are close together and so nice. But then you have other groups, it's a little bit different, wherein you have polar molecules, and that comes under a category called paraelectric, where they're coupled up, but there is a little polarization built into the relationship. I'm pushing this analogy pretty far here. But they're little couples, and we call them dipoles, and they are polar. But they are, with relation to each other, the couples are uncoordinated until you put on some electric field, in which case put on an external electric field, there will be some lining up of these dipoles with respect to the external field. But in the zero field, they have no net field around them. Here, once you put this on, this thing attains a fairly strong external field. And then the third category, the one that is not mentioned in your book, well, I don't know if the book even uses the word paraelectric. They do talk about permanent dipoles. Permanent dipoles. See, these are couples where there is some polarization. They may not be living together or something like that. Then we had the third category, which it turns out to be very interesting too, and these are those that have some built-in large-scale polarization. Namely, the plus and minuses are permanently built in, something like this. And it's organized, and they align each other. And a material like this, even in zero field, will have some external field. And as such, it's a technologically somewhat interesting material. Now let me mention a couple of other things which might follow from this. If you have a structure like this, suppose you vary the temperature of this thing. So you get sort of thermal expansion. You can imagine that thermal expansion might change the polarity, the amount of dipole. So you might think, and you would be right, to say that a thermal effect or temperature might affect this, and that is a class of materials, interesting, called pyro. From pyro is like heat, like pyromaniacs. Pyroelectrics exist, where they will change their electrical field with temperature. So in case you need a material like that, they exist. You could also imagine that if I squeeze something like that, I might change the dipole moment also, because I'm squeezing maybe the pluses with respect to the minuses. So the dipole moment might change. So then there might be not only a thermal effect, but there could be a pressure effect on such materials. And that exists also. You may have heard this, piezoelectric. Piezo meaning pressure, electric. And you could see, just intuitively, why squeezing this, changing its shape in some direction, could change the electric field coming out. Or, contrarily, if you put this in an electric field, its shape might change. And that was used in the old phonograph record, needles, where you have a needle, and the needle would ride in a groove, and as it bounced up and down, you're exerting a little pressure on a piezoelectric element, which sends off then a little electric field, which represents the sound. So the piezoelectric material was a way of converting the bumps in the grooves to sound. So you use a piezoelectric, the pressure thing. So there's this whole range of materials that I should mention to you, because it's good to know vaguely. You may not remember this forever, but it's maybe in the back of your mind, in case you ever need something like that, you can look it up. And I also mentioned, I think very briefly, that there's another kind of material that people use, which is they take some kind of a plastic and they shoot electrons into it. And somehow the electric charge stays in this plastic, and the material itself then has electric fields. Let's say you put in the minuses here, they will have fields like that. And they're permanently charged. And this is a material called an electret. Electret. Of course, what they're trying to give you the feeling for is a magnet. A magnet. See, a magnet is has field coming out of it, sort of naturally. Here, the electrets, they have sort of artificially put charge into them. And these guys are very interesting. We'll see later how they might work. And I think I mentioned to you, do I have this on? Yes. This microphone, and a lot of the microphones that are used these days are electret microphones. Because what they've done is they put this charged material near some other conductor here, And when my sound voice pressures jiggle the electret, the field coming from the electret affects the conductor nearby, and they carry that signal off and they amplify it, and then they can record, or like in this case, goes through a microphone. But my voice is jiggling a piece of charged film, which is changing the current in a conductor, and that's being amplified and goes through a speaker. And that's what is being broadcast here or recorded. So these are very interesting materials, and again, you can understand them on the basis of the straightforward ideas that we've had so far, even in Chapter 1. That's how powerful Chapter 1 is, because it has all those features of the charge, the forces that the charges act on each other, and the description of that force as an electric field. Okay. Now, I wish we had more time to talk about these things because, frankly, I think they're very interesting, but we have to move on. And so I want to then move on to Gauss's law, which is very straightforward, but it's a useful thing to solve certain problems, and it gives you also a little insight into the electric lines, electric field lines. So again, I break the chapter down into the key ideas. We have to understand the concept of electric lines and electric flux. You just got to learn those words, what they mean precisely, okay? Those are the key words here. And then we see how Gauss's law works. What it does, it relates, as you might expect, the amount of charge to the total amount of field coming out. That's all it is. Clearly, if you make more charge, you'll make more field. And the idea is to find the relation between the global amount of field and the charge that's sort of inside some surface. And once you get that, it turns out that you can actually calculate what is the electric field at a point very simply. Whereas in the Chapter 1, I didn't even do it in class, but you need to do some pretty fancy integrals, for example, to get the electric field due to a complicated charge distribution. Like, for example, I think there is the example of a line of charge. In other words, a smear of charge put on a line. And the book shows you how, if you want to find the electric field here, and there's charge spread out over this, how to do it. And it's doable with a little calculus. What you do is you take a little piece of charge here, and you imagine that's your source, dq, a little bit here, and you find the electric field that this charge produces here. Let's say this is plus. It'll produce some electric field in that direction. Now, in a case like this, there's some symmetry here, because around this point, the line goes equally in each direction. So you could find a charge here, which is equally distant. Let's say at a distance x. Let's go to x the other direction and pick the same amount of space, or dq, and find that charge and its field going that way. Now, the reason you do that is because since these are equal in amount, and we've chosen them to be equally to the side of our interest point, these sideways components cancel out, so that you're left with just the vertical components. The vertical component of this fellow plus the vertical component of this one is this. So when you add these two together, you get the total like that. And then in the book, what you do is you just add up all the symmetrical charges, but they're all now a little bit different. And it's an integral, and you look up the integral in the back of the book, and you get the answer, right? It's in the book. Now, that's how we would do it in Chapter 1. It turns out that with Gauss's law, as I hope we'll have a chance to get to, you can answer that in about 3 steps with no integrals. And that's one of the advantages of the Gauss's law. Some problems, the very, very symmetrical ones, you can get an answer for the field at that point in about 3 steps and hardly any thinking. And the symmetrical cases that are amenable to that treatment are a point, a sphere, a cylinder, and a plane, all of which have a lot of symmetry. And you use the symmetry, as we'll see. And the other thing is, so knowing the charge, you can get the field, and we can turn it around. And in the case of conducting materials, it'll turn out that we know the field, and so you can go backwards and get the charge, because the two are related. So depending which one you know, you can get the other one. And that's sometimes very powerful. So let me go on to... so the idea is simply that in Gauss's theorem, what you're doing is you're saying, if I know the charge, I know that the total amount of electric field coming out of the charge. One very homely analogy I use is like if you knew how many quills there are on a porcupine, I don't know what a porcupine exactly looks like, but if you knew how many quills there were on a porcupine, let's say there's, 100 quills on a porcupine. If you count the quills, you'll know how many porcupines you have, right? So if you put a surface around here and I count the quills coming out, I know how many porcupines I have. So if I had 2 of them, and they're the same, we're assuming these are physics porcupines. They're pretty much spherical and they have the same number of quills. That's the way physicists think. So if I count the number of quills, if I count 200, I say I have 2 porcupines. Okay, so that's what Gauss more or less said, I guess. So the point is, yes, so if the idea is that if you have a certain amount of charge, and if you count all the lines coming out of that charge, by putting a closed surface around, you don't want to have any openings where you miss some quills. So you have a closed surface, and you just count the amount of lines coming out. You can tell how much charge was inside. That may not be too surprising, but that's basically what it is. So if you have a closed surface and you see quills coming out, you have to know that they're coming out. If there are quills coming in, it means the porcupine's on the outside. So you have to know which way the quill is pointing. So if you see net amount of quills coming out, you know that there's somebody inside. And in electricity, you can have lines coming in, like a negative charge. We have this convention that lines go into the negative charge. Again, if you put a surface around here and you see a net amount of lines going in, you would say there's a negative charge inside. So the trick is to count the lines and see whether they're going in or out. That's it. That's all Gauss says. Now, sometimes you could have a situation where there are lines coming in and lines coming out, and they may add up to 0, in which case there's no net charge inside. Now, for example, our familiar case of the dipole. In a dipole, the field distribution is rather harder. The electric lines are going from plus to minus, you recall, and they bulge out. They look something like this. right? Remember that, okay? Like that. Around, and they go back into the negative, right? That's our dipole. Now, if you put a Gaussian surface, a Gauss surface around here, you will have as many lines coming out as you have coming in. So the net amount of charge inside that will be 0, because that's, in fact, what it is for a dipole, the net charge. There could be pluses, there could be minuses, but Gauss's will tell you net how much there is inside, plus or minus. Now, if you put your Gaussian surface in a different way, and by the way, you can pick your Gaussian surface depending on what you want to learn, but if you want to, for example, put your Gaussian, pick a surface that looks like this, suppose I put my surface here, and I count all the lines. Well, there are lines coming out, and there are lines coming out. So if I put my surface that way, it's going to tell me, yes, you've caught a plus charge, because I put the surface here. On the other hand, if I put my surface a different place, so it depends where you put your surface, what you're going to get. Somebody stole all the colored chalk. Ice probably did it. So, for example, if I had put my surface here, a closed surface, like a bubble, around that particular part, I would have captured lines coming in. See lines coming in, lines coming in, lines coming in, lines coming in. Tells me there's a negative charge inside, because I put the surface that way. And so depending on where you put the surface, you're going to get different answers, and it's always going to tell you how much charge is inside. That's it. Nothing hard. Okay, so let's see. So this picture says, and I think the same thing. If there's a charge, then the total amount of E, that you count the number of quills coming out, and that will tell you how much it is. And the way that we count the quills is we multiply the number that we see, the amount that we see, times the area. Now it gets a little bit tricky. Let's put the minus back. And so the lines are coming in. Now, what we want to do is we want to put a surface around a bubble. And in fact, I'll explain what is a bubble in the next slide. You see, you have to have a closed surface because you don't want any of the bubbles, any of the lines to sneak out. So, for example, a sphere like this is an appropriate surface. But a flat surface wouldn't be good because if I put my charge above here, some of the lines go through the charge, but some of them I don't capture. So you have to have a closed surface around the charge. Closed surface. But again, what surface you choose is up to you, and you just try to make life easy for yourself. You choose the appropriate surface, as we will show. So we have a closed surface, and we count the number of lines coming through the surface. Now, the reason this is good, why this works, is that Coulomb's law. Now, this is the simple derivation of the Gauss law. You see, Coulomb's law gave us that the force was K, the constant of proportionality, Q1, Q2 over R squared. And from that, we derived electric field, saying, well, it's the force, the electric field is the force on, say, Q2 due to Q1, and that is K Q1 over R squared. So that's the electric field, say, at some point R away from the charge. This would be our Q1. Right? Okay. Now, suppose, you see, Gauss was a brilliant mathematician, But you don't have to be a brilliant mathematician to do this. All you have to know is a little geometry, which you already know. And you know something about the geometry of spheres. If you have a spherical surface, well, two things we know about the spherical surface. We know its surface area. If I remember rightly, it's pi r squared. Okay, or is it 4 pi r squared? 4 pi r squared. And its volume is 4/3 pi r cubed. So that, so knowing that, Gauss did a very simple thing. He said, if E is a certain value at this radius r, and it's the same value, of course, the magnitude is the same. At every r, it has the same value. So let me multiply that by the area of a sphere passing through that radius r. So let me just multiply E times the area of a sphere and what you get, well, let me rewrite this in another. Remember, we could rewrite this constant k as 1 over 4 pi epsilon naught. It's just another way of writing that constant. So, and now you'll see why we do this, because that 4 pi is going to get out of there. Q1, 4 pi epsilon naught r squared. So let me just write, so this is the E everywhere on that sphere, all pointing out. Let me just multiply by the area of that sphere. And I get Q1, 4 pi epsilon naught r squared times the area of the sphere, 4 pi r squared. Miracle of miracles. The r squares cancel, the 4 pi's cancel, and you get Q over epsilon naught. So Gauss said, well, that product of the electric field times the area of the sphere around it tells me the charge inside. It's that simple. In other words, this is a way of counting the quills on the porcupine. Just multiply the amount of so this is kind of a density of lines. It turns out one way of thinking of it, in other words, it's like the density of quills, and you multiply by the area times the density, and it'll tell you the number of quills. So this is sort of tells you the number of lines, which in turn is telling you the amount of charge inside. And that's what it says. If it looks easy, it's correct. That's correct. It's too easy, right? You're suspicious when things get too easy. It's probably good to be suspicious. But in this case, easy is good. So then we do some fancy footwork. And we say, what do we mean in the book? They'll say, well, how do you do this actually? See, what you're really doing is you're saying I have a field coming out of this area. How do I exactly, suppose the surface were more complicated. How would I handle this? And the way you do it is by taking a little patch of area, dA, and what you want to know is how much of the field lines are coming through that area. You're trying to count the number of quills coming out here. And to do that, we do this mathematical thing. How do you describe, like, for example, I have a bunch of lines, and I want to know how many are passing through an area, let's say an area that big. Okay? Now, it depends, you see, on the angle that I put the area. For example, suppose I have those lines, and I put the area this way. Not many lines are going to go. I think I have my trusty something or other. Yeah. Scientific tool. Here's an area. If I have a lot of lines coming, and I say how many are passing through this area, if I line them up this way, nothing passes through. They miss. Whereas this way, things pass through. So you want to have something to tell you at what angle is this area, right? Because here at this angle, I get nothing. At this angle, I get all of it that's possible. This is even, again, it's too little. I'm missing some. So now the question is, how do I represent the angle of this area? Now, your first inclination is to say, well, call this the angle, the plane with here. But you see, that doesn't work too well. Because what's the vector here? In other words, if I have an area, could I call that a vector? You know, I'm trying to describe the direction of that area. How do I describe the direction of the area? See, if I put a vector to give it a direction, if I put it in the plane, I could put it anywhere in the plane. So it's not very helpful, because why did you pick that direction? So what the mathematicians have decided, let's be smart, let's put if that's an area, let's call that the interesting direction, because that's unambiguous, especially if it's part of a closed surface. Then you could say the direction of the area is the normal, that is perpendicular, direction to the outgoing, see if it's a closed surface, you know which is inside and which is outside. So it allows you to say, okay, this is my outward going normal, they call it. You may have come across this word in math someplace or other. So it's called a normal. I don't know what is abnormal in this case, but that's the normal. So at least you can tell whether it's going inside or out. So for example, if we had a patch and something were going into the closed surface, we would say it's a negative. You know, at least we have a direction. And that really, this is not a good way to do it. So it's a little bit hard to figure, but it's pretty foolproof once you get it. So for example, we put a normal here on that area, and we have a normal on this area. So when we say when the normal is perpendicular to the lines, nothing gets through. And the way to describe it, actually, is by saying, let's look at it sideways. Here are your lines trying to come through. Let's maybe make it larger. Suppose this is the normal to that area, and this is the direction of the electric field. So if this is the angle of the normal with respect to the electric field, that's the same as this angle here, right? Because as that one turns, this one opens up too, right? So this is also theta. And if this is the area, the amount of lines coming through is this much of the area, right? It's this component of the area. So we want to have this component. And this is the total area here. So that's this angle. This is the same angle, right? This angle is this angle too, right? So the area that we're interested in, which is the area perpendicular to the flow, this area here is the total area times, you see that is this area to this is the cosine of this. So A over A of interest here to the total area is the cosine of the theta. So the outcome of all that is that if you have a funny-looking surface, the product of E times area locally is E times A, the total area, times the cosine of theta, where theta is the angle between the normal and the electric field. That's what I tried to say here. Theta is the angle between the normal and the electric field. So that's the fancy way of doing it. Now, in fact, it's not that it is just that complicated, but we avoid complication by using our brains and try to do simple cases. Namely, the two cases that are really interesting are when the area is, the normal is parallel to the electric field, because then cosine theta is 0, cosine theta is 1. So what you have is E times A. That's easy. It's E times A, when the normal is parallel to the field. On the other hand, the case that we also like to do is the other one where the area is this way and the normal is that way, perpendicular. And in this case, the angle is 90 degrees, and the cosine of theta of 90 is 0. So as we said, nothing passes through the surface. No lines pass through the surface. So what we try to do is set up things so that we're either in this case or in that case, and we make life simple for ourselves. Just a matter of being smart about doing things. And anything more complicated than that, you do it by computer, or you ask some friend who enjoys this kind of thing. But we won't do it in this class. So that's what this slide has. Basically, the idea is try to get E parallel to N, and then your cosine theta is 1, and you just have E times the area. Or try to get E perpendicular to N, cosine theta is 0, E dot A is 0, and your life is easy. And then the trick is, if you have some complicated closed surface, at each little point you have to find the E and the N, and you do the cosine theta, and that's your answer. And we call that quantity, that E times A, is called the electric flux. It's the amount of stuff passing through the area. It's a little bit tricky word because there's nothing really flux you usually think of as the flux of time, something moving. It's not moving, it's just flowing. It's just the lines coming out. And again, here is a case in point of a point charge, and the electric field, this is pretty much what I did right from the start. We see the electric field from Coulomb's law right there, E is Q over R, over 4 pi R squared. Then now the next step is just pretty much what I did. Here's the E at a point R, and the area, in the case of the sphere, the outward normal to a sphere is along the radius, right? So N and E are parallel. Bravo, that makes life easy. That's this case. Cosine theta is 1. So you just take E times dA, and the angles are taken care of in the case of a sphere. Because A, the element, is parallel to the normal, and E is, in the case of a point charge, E is the same at every distance. Again, by symmetry, there's no reason why the field should be different at a different, it differs in angle, but at the same distance it should be the same by symmetry. So you get area, and you just go through this. It's pretty simple. So, again, that quantity, E times A, of over a closed surface, will tell you the charge inside divided by this epsilon naught constant. And that's it. It's just a way of finding the charge inside. There was a prize fighter who said, I think it was Joe Louis, but back in the day, where he was fighting some guy who was very quick and was always, Joe Louis could never reach him. And Joe Louis said before their last fight, he can run, but he can't hide. And so it's true here. The charge can run around, but it can't hide. If you catch the lines, you'll find it. So it's the net charge inside. And here's the law in all its glory, that integral of the charge over the whole area of a surface, that's what that circle means on the integral, is go over a surface, catch all the lines on that surface, multiply by the area. It'll tell you the net amount of charge inside. And, okay, so why do we bother? Well, again, you can find, as I said, if you know the charge distribution in certain cases, you can find the electric field without too much fuss and muss. Maybe I should do the last one of these. I have some examples of how it's done. Let me see if I can find the one with the line, because we talked about that. Look at all these you can do. Line. Yeah, this is the line symmetry. Remember, we started talking at the beginning of the class about how much time? 5 minutes. Let's do. Remember, we talked about the line, and we said that if you wanted to find the electric field here, you'd have to add up all the little charges, dq over here, and then you try to balance it out with dq over there, and you find the E, and you add, and you integrate over all the charges, blah, 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 blah. That was hard. Okay, so let's see how easy it is with Gauss. Gauss says that the total flux will be equal to the integral of the E times A over a closed surface, and that'll tell me the charge inside. That's what Gauss promises. Okay? So, let's do this problem. I have a charge. Now, the way that this was set up, there is a line of lambda is the linear charge density, known as. What does that mean? It's the charge per unit length. In other words, I have a certain number of coulombs. I spread them over this length. So it's Q divided by the length. So in each little element I have, for each little length, is lambda. Lambda is, you see, we have the Greek letter lambda. We'll also have later the Greek letter sigma for surface charge density. I don't think I'll get to that today. Sigma for surface. But L, linear charge density, is usually symbolized by lambda. Okay, so what we do is I think I can do this we have 5 minutes. So I have this thing, and I have lambda per unit length here. So what you do, you look at the symmetry of the thing. It's a line. So what's a symmetrical thing around a line? Basically a cylinder. So let's put a cylinder. That's our so-called Gaussian surface. We choose it just to be smart. See, and we have a cylinder centered on the line. And see how nicely this helps us. It's an open cylinder. Now you see what we have here is that we want to get the surface to be either parallel to the electric lines or perpendicular. Now, what direction would the electric lines have for a line of charge? I think we did that with the bristle brush, right? But for the bristle brush, looking at it edgewise, it's just going out like this, right? It must be, because there's no direction preferable one way or the other. Looking at the end of it and looking at it this way, the lines must come straight out also by symmetry. There's no reason why they should point one way or the other. Do we agree on that? So we can say that the lines are coming out of this perpendicular. It's hard to draw in 2 dimensions, a 3-dimensional thing, but I have my bristle brushes someplace, I think. Do I have to bother? Here, this guy. All right, so by necessity, along here, the lines must come out, and if this were infinite, there's no reason for them to go this way or that way, so they go perpendicular, and also they're equally going in this direction. So the natural thing to do is put a cylinder around here and catch all those lines. And the beauty part is that if I put the cylinder this way, these bristles are either perpendicular to the surface of the side, or if I cut my cylinder, now the bristles keep going everywhere, but if I put my Gauss surface with a perpendicular thing here, those lines, the last line is perpendicular to the lids of the cylinder. The lids are this way. The sides, the normal is this way on the, what should we call that, the can side, and this we could call the lid side. So the normal to the lid of the can we're imagining is perpendicular. So there's no flux through here, through the can that I put around here or here. So there's no flux through here, through the lids, and there's no flux through that lid because it's perpendicular. So the only flux is through the sides of the can. And so at a certain point, there will be electric field. We don't know what that is yet, but Gauss is soon to tell us what it is at a certain radius r. And Gauss says if I take that E, which I don't know yet, multiply it by the area, it will tell me the amount of charge inside over epsilon naught. Now, what is the area of that can? Well, the circumference of the can, if that's r, the circumference is 2 pi r. So that's the circumference. Then you multiply by the length of the can. So that's the total area of this can here. So I put that in. E. So I'm actually doing this integral in my head. So it's 2 pi r. That's the circumference of the can times its length. So that's the area of the can. And that's going to be, by Gauss, it's going to be equal to the charge. Now, what's the charge? Sorry about that. Can you guys see anything? No. What is that? See Van de Graaff. Okay, so that's equal to the charge. Now, what's the charge? Well, the charge is the amount of charge on the wire. See, the charge captured by that can? The charge that's inside the can is the length that's inside the can times the density inside, like lambda. So the charge inside, Q, is equal to the charge per unit length times the length of the can. Right? You get that? Charge per unit length times the length gives me the charge inside. That's the charge inside the can. So I put that in Q, Q, lambda times L over epsilon naught. So by choosing that nice geometry, the L's cancel out, and I get that the electric field is equal to lambda over 2 pi r epsilon naught. No integrals. The integral I did in my head. I just multiplied E times an area. And in some places, at the lids, they were 0. Et voila, finished. No fancy intuition. I didn't have to go to the back of the book. Nothing. So that's powerful. I mean, and you can do the same thing. If you go into the book, you'll see the other cases. Maybe we'll work them out later. And I think time is up. Pity, because we have some nice demos. I'll show you next time. Have a good weekend. Don't work too hard, but have some fun. Fun in the sun. Questions?